we'll be practicing balancing reactions. Let's get right into it. In the first equation we see here, the first thing I want you to do is take an inventory of the elements that are listed here. All right, on this side, my inventory includes lithium, hydrogen, and oxygen, and I write them in the same order over here: lithium, hydrogen, and oxygen. Next, I want you to count how many atoms of each do you have. I have 1 lithium, 2 hydrogens, and right here, 1 oxygen. In the product side, I have 2 lithiums, 2 hydrogens, and oxygen, I have 1. And we clearly see that I don't have the reactants equaling the number of atoms in the product, so we have to balance this in order to make it satisfy the law of conservation of mass. Things we're allowed to do are put coefficients in front of each of these elements or compounds, and I have 4 locations that I can put a coefficient in. The coefficient is nothing more than a multiplier. Okay, we're going to use these multipliers in order to balance the chemical reactions. So I'm going to start off with lithium. I have 2 lithiums over here. I have 1 lithium over here because the subscript is going to be 1. So I'm just going to say 2 times 1 will equal 2 atoms, just like right now it's a 1. If there's nothing written here, it's a 1. 1 times 2 is 2 atoms. Okay, so lithium has actually now gone from 1 to 2. And I compare the two sides. That looks like they're balanced right now, which is great. Hydrogens. I have 2 over here, and I have 2 over here. So far they're balanced as well. And the oxygens, 1 and 1. So as I see here, the 2-1-1 combo is the same as the 2-1-1 combo over here. I have balanced my chemical reaction. I'm going to put 1s in here as the coefficients or the multipliers in order to satisfy this. So I have 2 lithium atoms that will react with 1 molecule of water to produce or create 1 compound of lithium oxide and 1 molecule of H2. It's nothing more than a chemical recipe. Any point during this video, guys, please press pause, try balancing these equations on your own. I'll come around on the other side and help you. Yes, there's blanks here. There are some blanks. These blanks are the same places you saw last time. Sometimes I include blanks, and sometimes I don't. Let's take a little inventory of what's going on here. We have iron, we have sulfur, and we have oxygen. I have 1 iron atom. I have 2 sulfur atoms. That comes from this right here. And I have 2 oxygen atoms. All right. On the product side, I have iron, sulfur, and oxygen as well. I have 2 irons. I have 3 oxygens and 1 sulfur. I just got those from the subscripts. Let's go ahead and balance. I'm going to balance the, I don't know. Anything we can do, there's any order. You can start here, 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 or here. So it really doesn't matter in which place you start. So let's just start right here. Okay, we'll do something different. I say I have 2 irons and 1 iron. So the irons are definitely out of balance. I have 3 oxygens and 2 oxygens. So if I'm going to balance these, the oxygens at least, let's work with them first. Oxygen, 2 does not go into 3 in a whole number ratio, but they do go into the number 6. And if I do 3 times 2, I have a 6 there, and a 2 times 3 gives me 6 oxygens. I'm going to change my oxygen right now to 6, and I'm going to change this oxygen to 6 as well. 2 times 2 gives me, though, 4 Fe's. So the number of irons I have has now been altered. I need to put over here 4 times 1 to give me 4 Fe's. But I want you to see, by putting 4 in front of here, that's also distributed to the 2. 4 times 2 gives me 8 sulfurs. And I need to make my change right here. It's actually an 8 now, 8 sulfurs. And I need 8 times 1 is 8 sulfurs. Boom. Okay, so 4, 8, and 6. 4, 8, and 6. Law of conservation of mass was satisfied. In this problem, let's check it out. I'm going to start off with my atom inventory, C, S, and O. And I'm going to count the atoms on each side. Excuse me. Ooh, made a mistake there, because carbon appears right here and also right here. So technically there are 2 carbons. Okay, sulfur, I have 2, and oxygen 1. So I definitely don't have a balance here. These are not balanced at all. I need to use coefficients to balance them. One advice I'm going to give you here is that I want you to see that carbon appears here, here, and here. It appears in 3 different locations. Anytime you see an atom that is in several different locations, you tend to balance them last. Alright, so I'm going to balance the easier ones first, the easier ones that are not used as frequently. I'm going to choose either sulfur or oxygen to balance first. Let's just begin with sulfur. I'll put a 2 in front of this to make it 2, because right now it's a 1 times 2 equals a 2 times 1. So I have 2 sulfurs now, and a 2 times 2 gives me 4 oxygens. Let's look at the number of oxygens now. 2 times 2 is 4 oxygens. I need over here 4 oxygens as well. 4 times 1. So 4 times 1 is 4 oxygens, and 4 times 1 is 4 carbons, plus this carbon right here, which makes it 5 carbons. On the other side, I need to make sure I have 5 carbons as well. And right now I only have 1. And if I put a 5 in front of here, 5 times 1 gives me 5 atoms of carbon. So really what I have here is that 5 atoms of carbon are going to react with 2 molecules of sulfur dioxide to produce 1 molecule of carbon disulfide and 4 molecules of carbon monoxide. Once again, key in on which element, if any, not all the time it happens, but if any times you have an element that appears very frequently, balance it last. The one that's used most frequently should be balanced last. In this problem, I'm going to make another atom inventory. Why don't you press pause, guys? Please press pause and just try this problem on your own. Even try the atom inventory on your own, too. I have 1 nitrogen, 3 hydrogens, 2 oxygens. I have 2 nitrogens, 2 hydrogens, 1 oxygen. All right, and so as we work this out here, I see, are they balanced? Are they equal? No, and I have to use coefficients in order to satisfy the law of conservation of mass. Let's just begin anywhere we want. Why don't we, in this case, begin with nitrogen. Here's nitrogen. There's 2 nitrogens here and 1 nitrogen over here. Well, I'm just going to do a 2 times 1 to give me 2 nitrogens. And that changes that number to 2. And 2 times 3 is 6 H's. So no longer have 3 H's, I have 6 H's. So now let's work with the H's. I have 6 H's. Let's go over here. Let's make it a 3 times 2 gives me 6 H's. H's are now balanced, and 3 times 1 is 3 oxygens. Awesome. And the nitrogens are balanced, but the oxygens still are not balanced, 3 and 2. All right, and we need to now obviously find a number that 3 and 2 both go into, and that's going to be 6. And this is going to alter some of my problems here. So my coefficients, 3 times 2 gives me 6. And I'm going to erase this now, guys. This is gone, and I need to put a 6 right here. Okay, so I'm going to take a pause here, do my atom inventory. 3 times 2 is 6. I have 6 oxygens. 6 times 2 is 12 H's. And I put that over here now, 12 H's, and 6 times 1 is 6 O's. It's getting a little crazy. All right, so the O's are balanced. The H's are not balanced. I have 12 over here, and I have 6 over here. So let's fix the H's. Let's make them 12. Okay, I need to make it a 4 right here. 4 times 3 is 12 H's. And 4 times 1 is 4 N's. And the last thing I need to do now is fix up my other N's, because the oxygens are balanced, hydrogens are balanced, and we can fix up the nitrogens right now because they're not balanced. I have 4 over here. I need to put a 2 right here. And 2 times 2 gives me a 4 nitrogens. And my equation is balanced. That was a really messy equation. Sometimes you're like that. If they are, just work them out. Your atom inventory is really a key to doing this problem well and making sure you're not making mistakes. All right, so once again, the coefficients or the multipliers are 4, 3, 2, and 6. That was a tough one, guys. In this equation, once again, you're going to see something happening, and that is that there is an element that appears frequently, and that happens to be sodium. It appears in 3 out of the 4 possible locations. Like I consider this location, this, and this. It appears in 3 out of the 4 locations. That means it's a pretty popular element, and we're not going to balance it first. We're going to balance it last. So I have Na as an atom inventory. I have nitrogen as an atom inventory, and I have oxygen. Right now there's 2 sodiums because I have Na1 and also Na1. And I add them together to make 2. Nitrogen has 1, oxygen 3. And what we're going to find out, guys, is that we don't have a balanced equation here. And we're going to need to use coefficients once again to balance it. But once again, please balance the element that appears most frequently very last. Let's get into it. This time, let's start then with sodium. I see 2 sodiums here, and excuse me, we're not going to start with sodium because it's used the most. In this problem, we're going to begin with either nitrogen or oxygen first because they're used least frequently. Let's begin with nitrogen. I have 2 nitrogens there and 1 nitrogen over here. Put a 2 right there. That makes this 2 plus 1 Na. That makes this 3 Nas. Okay, 2 times 1 N gives me 2 nitrogens, and 2 times 3 gives me 6 oxygens. Okay, so we've dealt with nitrogen now. Now let's deal with oxygen. I have 2 times 3, which gives me 6 oxygens, as we see over here. And right now I have 1 oxygen right there. So I need to make that a 6. 6 times 1 gives me 6 oxygens. Now, I have improved oxygen. It is balanced. Nitrogen is balanced. But now let's see what happens to sodium. 6 times 2 gives me 12 sodiums. I need 12 sodiums on this side. I only have 3. And so what I want you to see, though, if I put a number in front of here, I'm going to affect everything in here. Nitrogens and oxygens will change also. But I don't have to do that because I need 12. And the question is, what plus 12? What plus 2 will give me 12? And it's really going to be 10. 10 times 1 plus 2 times that is going to give me 10 plus 2, 12 total sodiums on this side. So the law of conservation of mass has been satisfied. The problem isn't necessarily the easiest problem, but it does work. Keep a good inventory, and you should be fine. Okay, guys, and once again, in this problem, you're going to see we have a very common element here that happens to be oxygen. I'll balance that last. This time I'm not going to do an atom inventory. I'm just going to work it without it, okay? Let's give it a shot. It'll be a little faster. I have 3 carbons. I need 3 carbons over here. 3 times 1. Carbon's done. I have 8 hydrogens. I have 2 hydrogens. I need a 4 times 2 to give me 8 hydrogens. Now let's deal with oxygen. 3 times 2 gives me 6 oxygens right here. Plus 4 times 1 gives me 4 oxygens. So altogether I have 10 oxygens. Let's put that right here. 5 times 2. So the coefficients are 1, 5, 3, and 4. Once again, pretty easy when you leave the most popular or most common element to the very end. In our last example here for the day, we're going to check this one out in the same style as last time. And once again, I'm not going to do an atom inventory down here. I'm just going to work the problem out. Maybe you're feeling a little more comfortable now. Oxygen is the most popular element here, the one used most frequently. I'll balance that last. Let's go to the carbons. Either a hydrogen or a carbon works fine. Let's go to carbons first. I have 10 carbons here because right now this is a 1. 1 times 10. And I'm going to put a 10 here. 10 times 1. They're balanced now. Hydrogens, 22. Ooh, 11 times 2 is 22. Okay, now let's go to oxygens. 10 times 2 is 20 oxygens plus 11 times 1. All right, that's going to give me 31. In order to multiply this by 2, I can kind of say, what is 31 divided by 2? And the answer is 15.5. Now, you're not done. You're not allowed to use a 15.5. You're not allowed to use a 0.5. But what you can do is to make that a whole number, multiply every coefficient by 2. When you do that, the coefficients become 2, 31, 20, and 22. And I know I've done a good job because I can't reduce those any lower. If I had an atom inventory, it would prove the fact that I have equal numbers of atoms of each element on both sides. Anyway, guys, that was a pretty good one. Hope it helped you. Have a good night.